Yeah, today I'm going to give you a really, hopefully nice kind of introduction to magnetometry and magnetochemistry. So we've had a lot of really excellent talks so far from both Franks and Serena and Demetrius and Maurice that have, I think, really laid the foundation for beginning to really look at how magnetic fields are used in experimental work. And so what I want to kind of highlight, first slide, every person has their own kind of preferred unit. So what I've done is I've converted Serena's EV to wave numbers because I'm a wave number guy. So that's why these values are maybe oddly specific. But what I want to kind of highlight is that, okay, if we think about magnetometry, magnetochemistry, well, where does that lie here? Well, I guess the answer is, well, it doesn't, because today I'm going to talk to you about a spectrometry, not a spectroscopy. Those are different things. Okay, so far we've been focusing so much on spectroscopy. Other examples of spectrometry might be like mass spec, okay, but that's not a spectroscopy. And same is true of magnetometry. But that confers a number of key advantages and disadvantages, right? So, magnetometry to me is something that you use alongside other techniques. It gives you pieces of the puzzle, better than other techniques and vice versa. And maybe when you have an array of techniques, you get a really excellent picture of the electronic structure of a given molecule or system that you're looking at. So with that kind of out of the way, I really kind of hate having to do this because, I think you guys have been kind of inundated with slides of equations and units and values flying around, but I absolutely have to talk about this. So we're going to be kind of using a weird unit system called the electromagnetic unit system. This is kind of a subset of a centimeter gram second type unit system. There are others like electrostatic units and Gaussian units, but EMU is the one we're going to use. And I think, especially in our introductory chemistry courses, we're used to SI units, but I promise you that the CGS EMU unit system is really quite convenient for especially molecular magnetometry. If you're more into materials chemistry, you will see people use the SI units, but just keep in mind that these unit systems have specific conversions between them. So this 4 pi comes from the fact that the permittivity constant in the CGS EMU system is set as 1, whereas that is not the case in the SI unit system, okay? And a couple other things. EMU is not a unit. And it drives me insane when I see so many things in the literature where they plot on an axis EMU. That means nothing because it means something in a completely different context for any given measurement. So I highly, highly, highly discourage using EMU as a unit, and instead to use these units that are already clearly laid out within the CGS EMU unit system, okay? But that said, even today in the practical, the software that you will use, if you're using the Mac and Linux version, see EMU. And just keep in mind that it has a different meaning depending on the context, and yeah. Okay, so the same is also kind of true when we think about fundamental quantities. So really today what will show up are the Boltzmann and Bohr magneton. I use the mu-b nomenclature. Frank likes the beta, but they're the same thing. And yeah, again, we're kind of using these weird CGS units. So you'll see energy units like ergs show up as opposed to joules, but really it's just a unit system. And again, like I said, this permeability, that is the key difference of where these factors of 4 pi come from. So what becomes especially important is if you look at something like a molar susceptibility, it's not just changing units based on the volume from cubic centimeters to cubic meters. You also have to account for this factor of 4 pi if you want to make comparisons to the literature. So with all that out there, what I kind of want to move to is I think something that most of us have probably seen, or at least been somewhat familiarized with in our chemistry educations. And that's kind of these two phenomena, right? We have this phenomena of paramagnetism, right? You can take liquid oxygen and you can actually pour it between the poles of a permanent magnet and see, hey, that's a paramagnetic substance. It's, sticking in between these magnets. On the other hand, water is a molecule that's actually diamagnetic, and if you apply a strong enough magnetic field, you can actually do something like levitate a strawberry in that field. You need a really, really strong field to do that, and we'll talk about why, but diamagnetism is actually quite weak compared to a lot of the paramagnetic phenomena you might be used to. But those are kind of, I think, the two like main everyday phenomena that we hopefully have at least seen at least once. And I'm going to go ahead now and just kind of shift gears and talk about, well, where did they come from, right? It's kind of cool. We can phenomenologically see that, but what's the origin physically of that? And, you know, Frank really did a good job talking about fundamental properties of electrons today, and I'll, you know, continue that same point, but a so-called moving charge generates a magnetic field. So you can kind of think of it as an analogy. Now, I have to stress that the electron is not actually spinning. It's just an intrinsic property of the electron that it has angular momentum. But if the classical analogy kind of helps you conceptualize why is that the case, that's the case. And what that means is that for a given spin up or spin down electron, that moving charge has an intrinsic magnetic dipole associated with it. Okay, so spin up electron actually has its north pole pointing down, and a spin down electron has its north pole pointing up. That has to do with the fact that the electron G factor is actually negative, which most people in chemistry don't know because we've chosen the positive sign convention, but don't get confused. It's not super duper important unless you're comparing like systems where you're looking at both like electrons and protons at the same time, which have opposite sign G factors. Okay? And the punchline is, okay, that's cool. You know, we don't really think about free electrons that often. As chemists, we think about unpaired electrons in molecules. So how about a transition metal complex, like a high-spin iron-3 complex, right? Serena already showed you ligand field theory and how to think about how you can generate these kinds of MO diagrams. And Frank talked about the fact that when you have a bunch of unpaired spins and orbitals, these spins couple together in such a way to generate a kind of Gestalt property, which is the total spin of the molecule, okay? And I'm going to represent that with this kind of bagel vector. And we're going to say that this total spin of this iron center is 5/2, right? That's just because we have 5 unpaired electrons. It's a bit more complicated, as Frank showed you, to actually derive that, but for all intents and purposes, you can usually kind of, in most cases, just look at it pictographically and say, I've got 5 unpaired electrons, 5 times 1/2 gives me a total spin of 5/2. That's not strictly correct, but it kind of works if you just want the total spin value for a given spin center. And let's go ahead now and think about, what does it mean to be paramagnetic? What is really happening physically? So this kind of total spin vector, you can imagine that this is my iron complex. You know, maybe these yellow guys are counter ions, maybe these purple guys are solvent molecules, but you know, maybe I have some solid state structure, and maybe it's a crystal, so it's ordered, and this is kind of easier to explain with an ordered solid, but everything I say applies to a non-ordered solid as well. And you can imagine that as long as there's no externally applied field, you know, these spin vectors can just be kind of randomly oriented whatever way they want to point through space, right? They're just thermally pointing wherever they want to point. But the minute you turn on a magnetic field, and let's say we point it, and I'm going to call the plane of the power point the z direction, okay? In this case, we have a s equals 5/2 system, so these spin vectors have extremely specific orientations that they may take depending on the ms levels that, you know, they're pointing in. And so I've kind of tried to replicate that here where, okay, this one's kind of pointing along ms plus 5/2, this one is as well. This one is maybe ms minus 3/2, right? And if you kind of add up all these spin vectors, what you see is that, one, you have a slight bias where I've kind of exaggerated it here with only 8 molecules, but if you were to look at a whole solid, you would see, according to Boltzmann statistics, right, depending on the difference in energy of the field you're applying, you'll get a Boltzmann distribution that dictates such that you'll have a slight excess of spins that are, in general, aligning with that field rather than against it, right? And so you kind of get this net overall vector that points this way, which means that you have a magnetic dipole in your solid, and so now it's going to interact with an external magnetic field, right? And with a paramagnet, as soon as you turn off that field, the spins go back to thermal equilibrium and just point again in whatever direction they're going to point. But that's kind of physically what's happening, right? This is also a magnet. It's taking all these magnets from the electrons and being a magnet as a molecule, okay, but a paramagnet specifically. We call that Curie-Weiss paramagnetism. It turns out, and I'll cover this in a later slide, there are other types of paramagnetism, but this is the one that I think is the most intuitively understood for chemists, and luckily it's the one that we're most interested in for most cases. I think the one that's a little harder to wrap your mind around is, what about diamagnetism? Where does that come from? What does that really mean? So I'm going to go back to electricity and magnetism 101, which you had in college, right? And if you remember, right, you can take like a permanent magnet, you can accelerate it, or I guess you can move it with some velocity toward a loop of wire, and that field, right, these magnetic flux lines moving through this loop are going to induce a field that acts against the magnetic flux as it's changing through the wire. So this is kind of a repulsive force. Okay. You can actually do that experiment in real life. You can take a cylinder of just copper, which is it's not, you can't magnetize it, okay? But you can put a permanent magnet through it, and Lenz's law holds, right? You can't change the magnetic flux lines going through that loop of wire. Now, it does ultimately change because we have things like thermal losses and stuff, right? If it was a superconductor, it would just levitate there, but it's not. So you will get losses, and that's why you need some sort of like velocity. It has to be moving, because if it's just stationary, then you won't see that effect. But what's cool about the quantum scale is, rather than like a loop of wire, basically the analog to that is an orbital. And I've picked my favorite one, the dz squared. You can pick your favorite orbital. All the orbitals contribute, okay? But what's cool is that you don't even need a velocity, because this orbital, if you will, if you want to make an analog to macroscopic classical physics, there's no resistance, okay? There's no losses. So the magnet just being nearby this orbital will mean that there's just a permanently induced field that acts against that external magnet. That is called Langevin or orbital diamagnetism. So the key takeaway from the intro of this talk, paramagnetism comes from spin, and diamagnetism comes from orbitals. It's really that simple. And what's cool is that everything has orbitals. So even materials that are paramagnetic still have a diamagnetic contribution. Okay? Everything has diamagnetism always, because everything has orbitals. Or if you're dealing with a metal, conduction bands, but that's basically made up of orbitals in the fundamental sense. And so let's go ahead and keep pushing on this. So as I mentioned earlier, right, each unpaired electron that has a magnetic moment, mu z, is what you can actually measure in the lab. Okay, so if I were to take a measurement, I would find that the magnetic moment of an electron is about 1.00115965 Bohr magnetons. Okay, we're using units of Bohr magnetons here. This kind of anomalous movement away from 1 is exactly how we know very precisely experimentally what the free electron G factor is, right? So people in the physics community have worked to measure this out to extreme precision. It's one of the most precisely known constants in all physics. On the other hand, this was supposed to have an animation, I apologize. What if I want to determine, though, a magnetic moment of a molecule? How do I handle that situation? Well, again, let's take a different example, like a high-spin cobalt compound. So it's going to be S equals 2, and here's my kind of overall spin vector representing that. You just basically take the magnitude of the total spin, multiplicity, take the square root, and multiply by the free electron G factor, and you get the so-called spin-only magnetic moment. Now, if you'll notice, the experimental value is actually a bit higher. That has to do with these kind of orbital contributions, which are not included here, but this is just a good first approximation. How do I understand, what am I seeing experimentally for this cobalt compound? Now, but here's the thing. We're not going to do a spectroscopy, and so we're not really going to be probing single molecules at a time. We're going to be probing bulk materials. So this is where it begins to make sense to define a magnetization of the bulk substance, okay? And what's going to happen then is we're going to define what's called the volume magnetization, which is just the sum of all these individual magnetic moments per unit volume. This is where these kind of weird units of cubic centimeters are coming from, by the way. It's an artifact of the fact that we're starting at a volume, a per volume type measurement. But as chemists, right, and this is the punchline, I think we're more comfortable in kind of the molar quantity world. So in order to get from a volume magnetization, we just multiply by the molecular weight and divide by the density of the material in order to get those units. And if you're an astute observer, you'll see, okay, I'm going to get out units that have cubic centimeters and moles in them. Now, let's go back again to my example. a paramagnet is something that ultimately gains energy in a field, and a diamagnet is something that loses energy in a field fundamentally. Okay? I do need to make a quick point in that, and I'm a bit sloppy about this, and most spectroscopists are. There's a key difference between the so-called B field and the H field, and they're related by this volume magnetization that the sample feels. The good news is that in a vacuum, B and H are more or less considered equivalently, so that's why we're a bit sloppy. But the key takeaway, as I said, right, a paramagnet gains energy in field, a diamagnet loses energy in field, so the volume magnetization is nothing more than just the first derivative of the energy with respect to field. That's it. That's really fundamentally what that is, that quantity. So what then is this so-called value of magnetic susceptibility? And I'll talk about what that means in just a second. The magnetic susceptibility is a quantity that's a derivative of the magnetization. So we're now dealing with a second derivative of energy with respect to field, fundamentally. And again, as I mentioned, molar magnetic susceptibility, you'll have these units of cubic centimeters per mole in our EMU unit system. You know, molar magnetization, you end up ergs Gauss per mole. And then the external field is in units of Oersted here, okay? And for small fields, you can approximate this derivative as just m divided by h. And I'll show this later, but that turns out to have a 1/temperature dependence. And so as chemists, we're often pulling the lever of playing with the temperature. And what that means is if the susceptibility has a 1/T dependence, you expect this kind of asymptotic relationship, right? This hyperbola here. Okay, so as you go out to higher temperatures, the susceptibility will go down. As you approach lower temperatures, the susceptibility will go up. Okay? Now, that is Curie-Weiss paramagnetism. There are other contributions. There's this Langevin diamagnetism that's present in all matter, as I mentioned. That has a negative contribution because it has the opposite sign, right? It has this opposite effect of paramagnetism. And it tends to be quite a bit weaker. So if I compare Curie-Weiss paramagnetism and diamagnetism, you'll see that we're a couple order of magnitudes smaller, you know, compared to the typical range of the bottom of the range of paramagnetic susceptibility. This depends on temperature, of course, right? So, you know, it's a little bit hard to compare exactly. But you'll notice that this is a temperature-independent term, okay? And so what we measure in the lab is always a function of paramagnetism, diamagnetism, and some other contributions, which I'll talk about in just a moment. But you always have to correct for all these other contributions if you want to think about the paramagnetic susceptibility, specifically the Curie-Weiss paramagnetic susceptibility. That's what we're fundamentally interested in from a chemistry perspective. Now, it gets quite a bit more complicated, and I don't want to kind of get too much into the weeds here, but essentially you have what's called Van Vleck paramagnetism. This is a temperature-independent paramagnetic term, which comes from second-order Zeeman mixing with low-lying excited states. So, you know, if you have excited states that are relatively low in energy, you'll have more of this term contributing. And that's, you know, kind of an energy range that's a little bit stronger than diamagnetism typically. And then if you have any sort of, you know, nanoparticles or like impurities in your sample that are nanoparticles or metals or something like this, you kind of get these other Landau and Pauli diamagnetic and paramagnetic contributions. These just have to do with the electrons in the conduction bands, and I don't really want to get into that because I don't want to focus on materials chemistry today. But the key punchline is that typically we kind of treat these paramagnetic terms that are temperature independent as one term called TIP, or temperature independent paramagnetism. So it's kind of a, you know, a bit of a hand-wavy way because we don't often, usually we don't calculate these explicitly, and we just look at our sample and say, okay, it has this much TIP. I don't know what exactly is contributing to that, but that's where it's coming from. And therefore, whatever's left over is the susceptibility I'm interested in, which is Curie-Weiss paramagnetism, okay? Now, and this is where I think I'm kind of making a anti-pedagogical slide in the spirit of Frank, but, you know, we can have an expression where we just figure out that the measured susceptibility is the molecular weight over the density times the first derivative of a field of this complicated expression minus the diamagnetic sum of all the, and then the Van Vleck. And, you know, if I go to an office of an experimentalist, they just laugh at me and then, you know, I leave and we're sad because we didn't get to collaborate that day. So kind of what we want is maybe something a little bit more practical. You know, that's kind of my view as an experimentalist. This is something for the theoreticians and the hardcore physicists to have fun with. Or if you're me and you like doing both, that's also okay. But I'm going to focus on the experimental aspects today. So the bottom line is this equation down here. The measured susceptibility will need to be corrected for diamagnetism and temperature-independent paramagnetism to get at the value we want. Okay? And we're not going to worry about metal impurities. So how do we correct for diamagnetism then? Because every single sample that you put into any sort of magnetometry measurement will always have diamagnetism. Well, and this is where I have to point out that my PhD advisor, John, used EMU, which I was sad to see, but it is what it is. So yeah, just know that this table is really cubic centimeters per mole, okay? Those are the fundamental units here that we're dealing with. But the idea is quite simple. You kind of have three different methods that you can use to kind of correct for this. And it's that the diamagnetic susceptibility is just a sum of all the diamagnetic susceptibilities for a given individual atom. You sum up all the atoms in the molecule, and then any sort of bonds between those atoms. And I also use the word motif because sometimes you'll see things like, for example, like a benzene ring has a specific diamagnetic susceptibility associated with it, okay? So you just have to sum up these individual contributions and you arrive at a pretty good idea of what the total diamagnetic susceptibility is. And these values are coming from a lot of different experiments on a lot of different molecules. They're not completely extensive, and we'll talk about that in just a second. But I want to highlight the other method, which is kind of the quick and dirty method, molecular weight divided by 2 times minus 10 to the minus 6. Okay, so if you're lazy, or maybe if you can't find a specific value of the diamagnetic susceptibility table that you need, you can try this method. So let's compare them and see how do these two methods handle diamagnetic susceptibility. Here's a work from my PhD in collaboration with Andrea Cornea's group in Italy at Modena. And so we're looking at this tetrairon compound. In this case, I chose the chloride today, so these axial ligands are chlorides, and it has these three equatorial ligands that bridge these 4 iron centers together. How do we account for the diamagnetic susceptibility? Well, okay, I have to first consider what goes into a ligand. So there are 15 different, 15 ring carbon atoms, so 15 times the diamagnetic susceptibility of the ring carbon atoms, plus 1, 2, 3 nitrogens in the ring, plus 2 chain nitrogens. Those have different values, okay? You don't handle all atoms the same. It matters what environment they're in. And then 1, 2, 3, okay, 11 hydrogens. Okay, we got all of the atoms, but now I have 1, 2, 3 pyridine rings, and then 1, 2, 3, 4 aryl amide bonds. So those are the motifs. That whole thing in parentheses is the ligand, and there are 3 of them, so I multiply by 3. Okay? And then I just say there are 4 iron 2s and 2 chlorides, and I add all that up, and I end up at about minus 535 times 10 to the minus 6 cubic centimeters per mole. That is the diamagnetic susceptibility that we would predict for this particular compound. And if, I just kind of want to drive home the point, what about molecular weight over 2? Oh, it did a pretty good job, we're done. I will say that it doesn't always line up, but maybe 90% of the time the quick method works, and unless you need to be extremely precise, this method is usually quite good. Now, I kind of want to throw a bone to the biochemists in the audience. Well, what do I do if I have a protein? Because, I can't take, photosystem 2, one of my favorite proteins, and we're going to start at the end of this protein and start, okay, there are 11 billion carbon atoms, and I add up all those, and okay, no, it's never going to work, and you're never going to find out. Plus, you don't even know how many waters there are in a protein, or how many, maybe ATPs are floating around and things like this, right? So it becomes incredibly kind of unwieldy. And on the other hand, well, what's the molecular weight of a protein? Well, again, for the same reason, well, there's maybe some waters around, so okay, it's not really a exactly defined concept like it is as easily defined anyway in molecular chemistry. So how do we handle that situation, right? Because it's clear that there are metallic cofactors out there and we want to understand their magnetic properties. Well, this is where you can just do an experiment. You can take an apo enzyme, so maybe you've taken photosystem 2 and you've removed the OEC. It will be fine because it's a rock, right? The OEC is pretty stable. And you just measure that apo enzyme. Or you can also take an enzyme homologue and replace things with like zincs and galliums and have a diamagnetic version of your protein, okay? and maybe some buffer of solution to kind of help everything out, right? And then you obtain chi-d experimentally. And then what you do is you measure your system of interest, and then you just subtract out the dimagnetism of the apoprotein. And that's how you handle that practically, okay? So that's kind of method number 3. That's about as rigorous as you can get if you're doing any sort of like bio-type magnetic susceptibility, bioinorganic susceptibility measurements. Okay. How do people measure it? You know, we talked about kind of how to correct for diamagnetism, but how do people handle measuring things? Historically, this was done either using what's called a GUI or a Faraday balance, but essentially it's kind of a similar idea where you just put your sample in between, you know, 2 magnets and measure some effect. In the case, for example, of the GUI balance, you measure how the apparent weight of a calibrated weight is changing, and you can use that to figure out the susceptibility, essentially. More modern, and some labs have this, are what are called Evans or Johnson-Matthey balances. It's essentially a similar idea, right? You just have a sample tube that goes in between a pair of permanent magnets, you know, that has some effect on some balance, and then there's another pair of magnets and some pickup coil, and then you have some calibrated reading of the change of the current in that wire, and that tells you, okay, you have this many Bohr magnetons, okay? It's quite simple and rudimentary. There's another method, and this is one I think a lot of people have done, or at least worked with people who have done it, and that's called the Evans NMR method. This is a bit more sophisticated, but experimentally the way you handle this is you have, you know, your compound in solution, that's this yellow one here, for example, and you also have in that some reference compound like TMS is quite common in NMR, and then you have some capillary inside the NMR tube, which is just the TMS, no compound, okay? And what we're going to do then is measure basically the frequency shift between the capillary and the sample and relate that to what's called the specific susceptibility of the solute. So now we're in cubic centimeters per gram. Okay, and then you can look at how concentration, you know, and densities of the solvent. Normally we're dealing with quite dilute solutions, so the density of the solvent and the density of the solution are typically close enough that you can end up neglecting that term because that will go to 0 or very near 0, and so you only need to worry about this particular term. And then you just correct for the specific susceptibility of the solvent you're working with, so that's this term here. And so if you do that, then you end up measuring something, and then you have to subtract out the diamagnetism with one of the previous methods in the slide, and you end up at a paramagnetic susceptibility, okay? And the measured chi here, you just multiply by the molecular weight to get back to molar type units, right? And yeah, I will just make a quick comment that typically with the Evans NMR method, people prefer this sort of mu effective type unit system. I'm personally not a huge fan, but there's really nothing inherently wrong with it. So if you prefer to think of things in terms of mu rather than chi, there's a square root relationship between those two quantities, okay? And we'll talk about this a little bit later, what all these constants are. But I want to get to an actual example. And this is from Tristan Brown, who was one of my predecessors in John Barry's group when I was there at Madison, right? So we have this diruthenium chloride compound. And if you count up the number of unpaired electrons and you make an MO diagram, you'll see there's a 2.5 bond between the rutheniums, okay? And what we see, though, is that the key punchline here says 1, 2, 3 unpaired electrons. So quick, what's the spin? S equals? Anyone? 3 halves, I heard it. Boom, exactly. It's that simple. Okay, and then we can look and say, look, the TMS peak of the capillary is at 0, but the TMS peak of my compound is shifted to 74.1 hertz. And then I correct for all that up here, and okay. And eventually I get to this kind of punchline here. For S equals 3 halves, I predict that, and I'll talk about this later, but we often think about not just susceptibility, but susceptibility times temperature, so chi-T. Okay, that is about 1.88 cubic centimeters Kelvin per mole, because we're multiplying by temperature. And what do we see experimentally with this frequency shift? 1.78. So it's clear that we have an experimental method that tells us, hey, look, we've got 3 unpaired electrons. There are some reasons why this deviates, and we'll talk about that later, but what this method helps you with is to understand something about your electronic structure, and that's what is the spin state. Okay, this is powerful. Oh, oops. I think this is broken. I need a new pointer. Oh, yeah, no one's ever made that joke before, so I'm glad nobody laughed, so my sense of humor usually has a 10% success rate. But the key punchline here is we have a little bit more of a modern method to do this. And the real advantage of squid magnetometry is that you have a lot more control, you have a lot more precision, and you have a lot more types of experiments you can do. Okay, let's talk about how it works. So SQUID stands for Superconducting Quantum Interference Device. I personally think that the acronym SQUID is a bit desperate, but the physicists are the ones to blame for that. But essentially what you do is you take some sample that you're interested in, and you put it in between these pickup coils, okay? And you apply a field to it. And you can scan your sample, okay? But these pickup coils are superconducting, okay? So we're in, liquid helium, and basically they go to these coupling coils, which are coupled to what's called a squid, okay? And this is under magnetic shielding, and then the response of that squid to this current will then be picked up by more coils and calibrated with some detection electronics. But that's the very basic experimental setup. And what happens then is that we see, as I scan my sample, we can actually see a voltage response corresponding to that sample. And then what we do is once we've scanned the sample, we center it at the maximum or the minimum voltage if it's a diamagnetic sample, but maximum voltage if it's paramagnetic, okay? And then this value here is calibrated in such a way that we have an understanding of how much susceptibility, or really more accurately, what is the magnetic moment that we are measuring at a given temperature. And so the amplitude of that response curve corresponds directly to the sample magnetization. And what is the actual size of the squid? It's no bigger than a US dime or about a 1 or 2 cent euro coin. So these are really, really small. And yet, if you go and see the instrument on our lab tour, you'll see it's actually this really big honking instrument, what's going on there. So the actual sample sits really far down in this big vat. This is actually an variable temperature insert, but there's a big dewar of liquid helium that is basically contained there. And then there are, the detection electronics. But the squid itself is extremely tiny, is what's actually sitting inside this liquid helium environment. But the good news is that with this variable temperature insert, we can vary the temperature of the sample while keeping the squid under superconducting conditions, which allows us to have control over the temperature of the sample. Okay? That's very powerful. Now, how do we think about susceptibility? I'm going to shift gears a little bit here, and I will try to not make it quite as mathematical as what we saw on some of the slides this morning. But essentially what we want, again, for paramagnetic susceptibility is a first derivative of the molar susceptibility with field. So it's magnetization, sorry, molar magnetization with field. But how do we get that molar magnetization? Well, in classical mechanics, I told you it's the negative first derivative of energy with respect to field, right? But in quantum mechanics, we know that we don't have a continuous set of magnetization. We have rather specific magnetic moments that are quantized. So these energies are quantized, which means that our life becomes a little bit more difficult temporarily as we handle that mathematically. So what we need to do is to use a Boltzmann distribution, and that's where that really ugly expression came from. I promise it's not that bad, though. This is just a basic Boltzmann distribution where you sum up all these derivatives and these exponentials, and then you multiply by the Avogadro constant to arrive at this in a molar quantity, okay? That's how we get there. But the problem is, what does this really mean, these quantized first derivatives? Well, I'm going to take a trick from statistical mechanics because, again, we're not dealing with molecules, we're dealing with an entire bulk sample. And I'm going to use what's called the partition function and define it as the sum of these exponential terms, these e to the minus en over kt. Okay, kt is just thermal energy, so we're normalizing that, right, for a given temperature. And what we can do then is say that the derivative of the natural log of the partition function is this expression. And I know you might be thinking, well, that doesn't look great. Well, I promise you it makes the expressions for magnetization and susceptibility a lot simpler. Now, you can also see that second derivative relationship of the susceptibility with field here. Okay? Magnetization is a first derivative. These are unfortunately still a bit difficult. I would even argue almost impossible to apply unless we make some approximations. So these are fundamentally always true, but we need to kind of play some mathematical tricks for the next few slides in order to have something that we can work with like pen and paper, right? Because we're experimentalists, and we want to be able to predict something in the lab. And it's nice to be able to turn to ORCA, and I find that very useful. But sometimes I just want to do my experiment and I want to understand what's going on in the lab. So how do we do that? So I'm going to make a couple approximations. The first is I'm going to do a Taylor series expansion of these energies, these quantized energies, and powers a field. So we have this first term, which is a zero field energy. And then we have first order Zeeman coefficients, second order Zeeman coefficients, and all these higher terms. I'm going to neglect anything above the second order. That's an approximation. And now I can take a derivative with field. Well, this term goes away, there's no field, so it's minus that, and then minus, oh, the 2 comes out front. Okay, so this is what the quantized magnetic moment looks like in that expansion. And again, all these higher order terms, let's ignore it. And it's negative, so that's why we have negative signs. And so now I can plug that back into this derivative of the natural log of the partition function with field and put that in right here where those quantized derivatives were, okay? That allows us to obtain a new expression for magnetization, and if you are an astute observer, you'll see that KT and KT are going to cancel, okay? So that's step 1. Step 2 is very important for what we're going to do today, and that's that we're going to be at fields that are very small and temperatures that are large enough, we'll say. Okay, so this quantity, field over thermal energy, has to be much less than 1. If we don't do that, then this approximation won't apply. You can still derive expressions, but we won't be able to derive what's called the Curie law. Okay, so this is actually going to be the approximation that leads us to the so-called Curie law, which is only valid for these conditions. Okay? And if I do that, I can just, again, do a Taylor series expansion of the exponentials and just drop all the higher order terms, which I was too lazy to write a plus, but that's basically all this is here. And so what you see is that we have only the first order Zeeman coefficient here, and the zero field energy and the exponential, and that's it. So that's a lot simpler than 25 terms. And if I plug those into those exponential terms, we obtain this. Now I'm going to distribute these, and so we have this expression here. So you'll see that there's this, I'm going to go to the next slide now because it's the same. You'll see that there's this term, En1. There's 2 terms that are linear in h, and then there's an h squared term, okay? Well, one thing that is true is that as I go to zero field, my sample has to have no magnetization. So we know that the limit as h goes to 0 of m should be 0. What that means is that this term has to be 0. It's not dependent on h, but if I'm at this low field limit, it has to be 0, right? So we're going to get rid of that term. I'm going to discard the quadratic h squared term because if we're dealing with a small field and then squaring it, we're dealing with a quantity small enough that we don't really care compared to the linear terms. So let's get rid of that one. Final one, I told you that h over kt is much less than 1. So in the denominator that matters because we have 1 minus a very small number. Up here it needs to be left alone because we don't have 1 minus a small number. So we're going to leave that alone. Okay, finally we arrive at this expression, the molar magnetization. And remember, susceptibility is just a derivative with h, so okay, we're done. That is called the Van Vleck formula. And this is kind of the key equation that a lot of people use to derive, how do susceptibility curves behave. And it's going to allow us to arrive at the Curie law in just a moment. And you'll see, look, all we have are the zero field energies and the exponentials. We have a term that's actually the first order Zeeman coefficient squared over KT. So there's some thermal component, okay? And then we have the second order Zeeman coefficient. That's it. It looks more complicated than it is, but there's really only 3 distinct energy quantities we have to actually think about in order to use it. So, as I just mentioned, right, first order Zeeman, second order Zeeman, and then the zero field energies. We don't need to calculate these ugly derivatives anymore. We've done it in a sense with approximation. I'm going to go a step further and say that just for the sake of argument and simplicity, if there are no low-lying excited states, then these terms are going to be incredibly small, and we can neglect the second order Zeeman term. So now we're at an even simpler paradigm where it's just the square of the first order Zeeman terms and the zero field energy terms in these exponentials, and that's all that matters. If you have low-lying excited states, then you absolutely have to include those Van Vleck terms, as we call them. So I'm going to call this, it doesn't really have a name, but I'm going to call it the Van Vleck formula, neglecting Van Vleck paramagnetism. So I always kind of laugh to myself about that. But Yeah, okay, so that's great. We've done a lot of math, but can we apply it in real life? We can. We know the Zeeman energies already. It's just these magnetic sublevels times G times mu B, and then the energies depend on the strength of the field, of course. And we know that these magnetic sublevels go, as Frank said, as a 2s plus 1 dimensional space, spin space of minus s to minus s plus 1, all the way up to plus s, right? That's the magnetic sublevel space of our spin space. And again, remember, we have these assumptions. No low-lying excited state, so no second-order Zeeman coefficients to worry about. And we're at small fields in relatively large enough temperatures, I'll say, okay? And so let's just say that we're going to set our ground state as a 0 point. That doesn't always apply, but I'm going to do that because that's convenient, and most people do. And then, look, this is just the Zeeman coefficient is msg mu b. That's the coefficient that goes into this energy expression for the Zeeman, the first order Zeeman. Let's plug them in. So if I do that, I have n over kt. I take the square of this, so ms gets squared, g gets squared, mu b gets squared, okay? And then I have these exponential terms. Now, if e and 0 is 0, then these are both 1. That's quite simple. So now I'm just dealing with looking at this guy. And if I do that, that's where the g squared mu squared comes from. So we have a collection of constants. And then we need to divide by the dimension of our space, so 2s plus 1. And then we're going to sum all the way from minus s to s of the ms squared. That's it. And if you remember from math class, which I didn't, so I always have to look it up, but there's a sum of squares formula, which is that the sum from 0 to x of I squared is x times x plus 1 times 2x plus 1, all divided by 6. If I sum from minus x to plus x, then this becomes a 3 in the denominator, because I'm doubling the total amount of the sum I'm doing. And so that's it. We get a 1 over 3, okay? ms squared becomes ss plus 1 times 2s plus 1, but we're dividing by 2s plus 1, so that cancels, and we're left with this final expression. That is the Curie law, named for Pierre Curie, the husband of Madame Curie, who's more famous than you probably know. They both shared the Nobel Prize in physics, not for this, but this is the fundamental Curie law that is quite common, especially if you just look in an introductory textbook. We kind of went through all these crazy steps to get there, but it's really elegantly simple. It's just some collection of constants, which we call the Curie constant C, divided by temperature. And this collection of constants, well, some of them are constants and some of them are not in this sense, right? The Avogadro number doesn't change no matter what system you look at. But, and this is kind of where I think you'll see this today, but also tomorrow in Alexander Schnegg's EPR, right? We know that we can experience G values in systems being perturbed from the free electron value. And the other lever we can pull is we can have different spins of our system. So those are going to be, G and S are going to be the two levers that we can pull that are going to control what the Curie constant size actually is. And if you prefer the kind of, a little bit, in my opinion, outdated, but still somewhat widely used mu effective units, this is the relationship. It has a square root relationship with chi t. So it's about 2.8 times the square root of chi t. I personally don't like those units, and I'll explain that in a moment why. But now, we finally arrived at something. I can now use different spins, so 1 unpaired electron, 2 unpaired electron, 3, 4, 5 unpaired electrons at a very small field and derive susceptibility curves. So you see all these beautiful hyperbola, okay? And cubic centimeters per mole versus temperature. But here's kind of the problem. If I actually measure something in the lab and I see these hyperbola, well, I mean, it's clear that the spin is increasing, but if I just have one sample, I don't really, personally, maybe you do, but I don't have a good way to just look at a hyperbola and be like, oh yeah, that one is 3 halves, that one's 5 halves. If I just saw one of these, I wouldn't really know that, right? So, what do we do? That's where chi t comes in handy, right? If we just multiply this by temperature, we're going to get rid of this asymptotic behavior, and we're going to end up at horizontal lines. And you can convert this formula. It's about 1/8 g squared ss plus 1. You can also think about it in terms of n, the number of unpaired electrons. But it's very simple. Chi t versus t gives you horizontal lines, okay, at least in the high temperature regime, with 1, 2, 3, 4, 5. So as long as you know what the value of chi t is, you know how many unpaired electrons you have in your sample, you know the spin state. That tells you something fundamental, a property about your sample, okay? And what I've done here is I've just given you, what's relevant for D transition metals, at least for monomers, right? But you can have 1 to 5 unpaired electrons, and so these are the kind of chi-t values, assuming the G value is the free electron G value, which may not be the case. But that's what these values would be if it were, okay? So we kind of know what to expect. One thing I don't want to go through the math of too much, but just to kind of highlight, is talk about magnetization. It follows these so-called Brillouin functions. So, you know, we've only really dealt with this kind of very low field, large enough temperature regime, but there are actual analytical functions that describe the entire regime that involve these hyperbolic cotangents and therefore hyperbolic cosines and hyperbolic sines, which I don't want to talk about, but I just want to kind of show you what that looks like. So, you know, I told you that the molar magnetization is equal to the susceptibility times field as long as the field is small and large enough t. And what I mean by that is that we're in these linear regimes way down here. But as you see, if I apply a field, eventually it starts to kind of taper off and then it saturates. Why is that? Well, you can't magnetize a sample infinitely, right? Eventually you run out of things to align with the field. Okay, so you can't go out to infinity here. If you go to infinite field, it's going to saturate. And depending on what units we write this in, you can divide by n and the Bohr magneton and see that these Brillouin functions level out at g times s. So if I'm dealing with s equals 1/2, I expect that, okay, g is about 2, so 2 times 1/2 is 1. Oh, okay, it levels off at 1. S equals 1 levels off at 1.5, right? And so on and so, 2, and so on and so forth. Okay? And if you go out to an extreme high field, you're basically just completely populating mostly one spin level, okay? To a good first approximation, because you're splitting these spin levels and the Boltzmann distribution will take over. If you add temperature, you can start populating higher levels again. So that's where things can get interesting, right? But here's the thing. Everything I've told you so far applies for systems that I would say are isotropic. So we've completely ignored zero field splitting or G matrix and isotropy, as Frank talked about this morning, right? What about all that? All those things cause deviations away from the Curie law, depending on the temperature. So let's look at how to deal with that. And this goes back to Frank's point this morning. Okay, so let's do my favorite example, high spin cobalt-2. So we have an argon 3d7, and then we look at the Russell-Saunders coupling, Ellis coupling, right, and electron-electron repulsion. We end up with these free ion terms, but then we go to ligand field theory, which Serena talked about, and we split into the tetrahedral point group terms, and you see that the quartet F9 splits into the quartet A2, but then we do another perturbation up, but then spin orbit up, and then Zeeman. And we can do that for every single state, and then, oh my gosh, you know, before you know it, you have a crazy dimension Hilbert space that you're dealing with. What the spin Hamiltonian does, and this is what Frank verbally said this morning, is to basically assume that as long as this ground state is separated well enough from these excited states, we can just kind of look at these guys that I've highlighted in blue and red, spin orbit coupling and Zeeman, and come up with what we call an effective spin Hamiltonian that models that system. Okay, and this is what we as experimentalists like to focus on, because this is a much simpler problem than I'm almost never thinking about the quartet P5 state personally when I'm dealing with high spin cobalt-2, because it's just way too high in energy for me to care when I'm doing EPR spectroscopy, right? Why would I bother doing all this when this is just fine? So as Frank mentioned, that's an effective Hamiltonian. Okay, we're going to model these energy levels with different Hamiltonians that arrive at the same energies that allow us to get useful information from our experiments. And I think Alexander Schnegg will talk about this tomorrow. You can go a step further. Like, say you have this Kramer system and these Kramer's doublets are well separated. Sometimes the EPR people will say, okay, the effective spin is 3/2. I'm going to pretend it's 1/2. That's called the pseudo spin. And I'm going to get fictitious, I prefer to call them fictitious G values. This is actually called effective G values in the EPR community, which is, in my opinion, a bit confusing because we're already dealing with an effective spin Hamiltonian. So I prefer to call those fictitious G values. But the point I want to make is never, ever, ever get confused between a G value of like 662. There's no such thing as a G value of 6. That just comes from pretending the spin is 1/2 when it's not. And that really large G value is correcting basically for the fact that we see the Zeeman splitting of a particular Kramer's doublet increasing at a certain amount compared to if it were truly 1/2. Whereas if you go to ORCA and you do a calculation, you'll see you're never going to get a G value out of 6 because you're actually calculating with the true effective spin. So just keep those concepts separate in your mind and you'll be good. It's quite confusing, but try not to get confused. There's no such thing as a G value of 6. You do get real deviations away from the electron value of 2, but not out to like 10. That is not physically real. Okay, so this is, again, just kind of a little bit of a recap of what Frank talked about this morning, but I can think about taking an unpaired electron and applying a magnetic field and seeing how these MS levels split out in energy. That's governed by this Hamiltonian. I prefer the mu b, but you could write beta if you prefer, okay? And then we have some matrix, G, not technically a tensor, that relates the electron's spin vector with the external field, right? And we can solve that to get energies. Well, we also have the zero field splitting Hamiltonian, and as Frank showed as SDS, D is the zero field splitting tensor. That describes kind of the internal magnetic fields electrons feel from two main sources, spin-spin coupling and spin-orbit coupling. For transition metals, in most cases, you can ignore spin-spin coupling unless you're dealing with something that's very high symmetry like manganese 2. Okay, if you have like a sextet as ground state, then yes, spin-spin coupling is going to be important. But for something like high-spin cobalt 2, you can ignore that and just think about the spin-orbit coupling contribution to a very good first approximation. But what this does is even without an applied field, right, we see that these MS levels, as long as I have more than one unpaired electron, okay, you get a splitting. So the MS plus minus 1 levels are, in this case, lower in energy because I've set D as negative. And so that's governed by the so-called axial zero field splitting parameter D, which is relating to the Z component of the spin. We add this constant term to make the tensor traceless, basically. And then you also have what's called the rhombic zero field splitting parameter E. This has to do with any time you have a situation where the XY directions are also anisotropic. Okay? That's going to come up a lot in the EPR talk tomorrow and in my practical today, but I just wanted you to see the forms of this. And if you look at my colleague Josh Telser has this nice paper from 2017. He's gone through and just kind of derived what these zero field splitting energies look like out to S equals 5/2, including rhombicity for you. Okay, this is the basic picture of how these MS levels are changing with the zero field splitting. Now, what I've done is I've gone a step further, and I've also just provided you here the actual matrices. So on the diagonals are kind of what we're used to thinking about, like the Z component of the Zeeman splitting, for example, but also these axial zero field splitting parameters. I'm going to ignore rhombicity here just for the sake of simplicity. And then we have these off-diagonal elements, and these come into play when you apply the field in the X or Y direction, for example. Okay? And I can do that for S equals 1, S equals 3/2, all the way up to S equals 5/2, you'll see that we have actually, it gets complicated quickly, right? But what we fundamentally do when we fit an experimental spectrum is we're diagonalizing these matrices and solving the system for its particular eigenvalues. This is how it works. So, I'm just only considering zero field splitting and Zeeman splitting here, but you might have exchange coupling, you might have other interactions. So, these matrices are not universal. It applies very much specifically to the system you're looking at. I just did it here for the sake of argument for zero field splitting, ignoring rhombicity, and then Zeeman, assuming the XY directions are the same, which they might not be. Okay, and so let's actually look then how, what does that do in magnetometry? Well, here's an example of an S equals 1 system where I've set the axial zero field splitting parameter as plus 20 wave numbers. And so at zero field, okay, you'll see that the ground state is 20 wave numbers below. It's positive, and so the MS plus minus 1 levels are up here in energy, right? And if I apply a Zeeman component, you'll see that the two magnetic levels are perturbed by that. The non-magnetic level has no change in the Z direction. On the other hand, if I apply the field along X in this case, you'll see actually that you get a quadratic dependence on field for the plus 1 and 0 term, and it's actually the minus 1 term, which is a constant value. Okay, and that just comes from solving these matrices I showed on the previous slide. But what I want to do now is not just think about energy. Let's think about what would that look like in an actual magnetic susceptibility experiment. What would that look like? Well, here's my matrix. And here's my Van Vleck formula neglecting Van Vleck paramagnetism. Let's plug and chug. So first of all, these Zeeman coefficients squared, that's going to be like mu bgz squared. Here's the first one. The second one doesn't have a Zeeman component, that gets squared. Okay, the third one is minus mu bgz squared. Okay, so we got that taken care of. Now let's add the zero fit splitting component, so e to the minus 1/3 d over kt. Okay, but then we have the minus 2/3. Okay, but this is a zero term. Okay, and then we sum up in the denominator. Okay, and so now we're down here. We've taken care of all this. This squared and this squared just gives you a factor of 2 up front, and then these are constants. So this is specifically chi in the z direction I'm looking at here, okay? That's why I only consider the diagonal elements in this case. And if I do that and I plug and chug, you end up with this expression over here. This is a deviation away from the Curie law because what it's telling you is that chi in a very specific direction does not follow the Curie law, it follows its own expression. And you could play the same game for the xy directions. I won't do it here, but the point I want to make is that if I look at what that does to the susceptibility curve, if it's plus 20 wave numbers, here's chi. Okay, chi z is in brown. It kind of follows a little bit this kind of Curie behavior, but then at low temperature, it goes back down to 0. On the other hand, chi in the xy direction goes like way up here. And then unfortunately I chose yellow, which was not the best color choice. But if you were to look at what we call a powder average, I'll talk about that in just a moment, you'll see it behaves like kind of somewhere in between these two worlds. And the same is true for chi t, right? You can see how the yellow curve, which is unfortunately really bright on the white background, I'll change that later. You can see the chi xy and you can see chi z. Okay, so we have a system with anisotropy because of the Zeeman, the zero fit splitting, right? This is how it actually impacts susceptibility curves. Using that Van Vleck formula I gave you, you can derive these expressions for any spin system you want. And fundamentally, when you do a fitting program, you're essentially doing that. But here's the problem. The yellow curves are probably what you'll see experimentally if you have a powder sample. And here's the problem. Chi changes in each direction. So I have to integrate over theta and phi. Okay, so that means I have to do this integration and I'll divide by 4 pi to normalize it so that my integral equals 1, okay? But I have to account for every single orientation. Okay, but it could also go in the z direction. So we're going to integrate over a 3D unit sphere. And I think Alex might or might not talk about this in the practical tomorrow, but it's certainly relevant if you are working with EPR spectrum and you're working with like knots. This is what I'm talking about. So how do we actually do this integration? It's extremely computationally intensive and we have to account for like tons of, no. It's much simpler. What we're going to do is what's called Lebedev quadrature. We're going to approximate this continuous integral with a discrete sum of grid points, okay? And I didn't want to really bog you down with math, but there's a really nice, really short Wikipedia article. It's like 5-minute read, 10-minute read on where you get these weights. That just has to do with certain polynomials and how you choose these grid points. But essentially what you can do is you can say, rather than integrate continuously, I'm going to integrate numerically and assign a weight for each of my grid points. And that's going to be enough to kind of sample accurately enough that I'll get a very good idea of what chi really is if I were to integrate it. You can use coarse grids, you can use really fine grids if you want to account for as many orientations as possible. One thing I've shown here is that you can do an octant of the unit sphere. You can also do a hemisphere, and I'll talk about that in just a moment. There are tons of grids out there. These are the Lebedev grids, which are excellent, but there are other grids out there that were great, and honestly, sometimes you might have a good reason to choose a different grid, which I won't really get to in the summer school too much, but if you ever do any serious spectroscopy, you'll have to consider how is my grid affecting my model. These are subsets, as you'll notice, of the full sphere Lebedev grids. These are octants, and this is a hemisphere. That just has to do with the symmetry, which I'll talk about in a second. But there are other kinds of grids out there. My program is using spiral grids as well. So if you want to sample orientations that way, you can do it. You can have a coarse spiral. You can have a very fine spiral that circles many times as you go up. But you're just sampling orientations and integrating here and integrating there. And you keep going until you arrive at a summation that is a quite good approximation. Now, when do I use an octant versus when do I use a hemisphere? That has to do a lot with the kind of symmetry you're dealing with. So I would say rule of thumb, there's no hard and fast rule, but rule of thumb, If you're dealing with something that's very axial, so the E over D, we talk about that as the so-called rhombicity parameter. If that's quite close to 0, that's the axial limit, right? If the XYG tensor, or matrix rather, is equivalent, you can get away with an octant grid, and then you don't need to integrate over the full sphere, you just multiply by 8, and you've already solved your problem. On the other hand, maybe you're deviating away from axial symmetry, electronically speaking, right? And maybe the x, y, g values are not the same. Maybe it makes more sense to use a hemisphere integration and then multiply by 2 to properly capture how these chi orientations are changing through space. This is important for magnetometry. This is important for EPR because EPR has a similar issue, okay? And EasySpin, if you've ever used that program, uses yet another type of grid called a triangular grid. All kinds of grids out there, they all have advantages and disadvantages, but this is kind of the key takeaway. Okay, so now I want, with all that out of the way, and let me just check how I'm doing on time. Okay, I have half hour, good. Let's consider what happens if I change the sign of the zero field splitting. So this is magnitude 20 wave numbers. If D is positive, that has a certain effect. If it's negative, it behaves radically differently, actually, right? And if I look at these in chi t, you can see how radically different they behave. And it's very unfortunate that I chose yellow. You can actually see this yellow curve seems to approach a finite-ish value as you go to, let's say, 2 Kelvin. It actually technically goes to 0 if you go to 0 Kelvin, but if you go to like 2 Kelvin, it's going to about like 0.4. Whereas if the zero field splitting is positive, the chi curve is going all the way to 0. So these chi curves behave the same at the high temperature, but when you're at low temperature and you're governed by having differences in the populations of the magnetic sublevels due to Boltzmann statistics, you end up with different shapes for the chi curves. And that tells you something about the sign of the zero field splitting. And this is a way we can look experimentally and have an idea, is the sign of the zero field splitting positive or negative? Now, before we go too far though, I do need to make a public service announcement. And it's that, yes, you can tell the sign of the zero field splitting. However, it's often in practice quite difficult. You can see, of course, for the high temperatures, it's not possible, right? You're completely overlapped with positive and negative values. It's only at these low temperatures that you see these radical differences in the chi t curves. That's public service announcement 1. Public service announcement 2 is that if you're dealing with s equals 3 halves, you can forget it. They overlap perfectly. So for that particular system, it's essentially almost impossible with susceptibility alone to know the sign of the zero field splitting. This has to do with the fact that you're dealing with 2 Kramer's doublets, and no matter if the sign is positive or negative, you kind of end up with a very similar expression for chi t. You can't tell the difference so easily. So really, like high-spin cobalt-2 is one of the most challenging systems to get that kind of zero field splitting sign information out of. And the other thing I would say is that these all, of course, assume no rhombicity. If you go to the rhombic limit, these differences become less and less until the sign of the zero field splitting has really no macroscopic meaning. It has a microscopic meaning in the spin Hamiltonian, but not any sort of observable physical meaning in the macroscopic world we live in. Okay, and so how about for s equals 3 halves? You gotta, what do we do there? You can do what's called these magnetization measurements. This is where magnetization comes in, and go on a reduced field axis to extremely low temperatures, and you do see some differences in these magnetization curves, but they are extremely subtle. And I would say, especially for the s equals 3 halves case, you must do another spectroscopy technique if you want to know the zero field splitting sign. You must. I would not rely on magnetometry alone in most cases, okay? For other spin systems, you have a bit of a better situation, but for s equals 3 halves, you're really out of luck in most times. So let's consider then how these magnetization curves look. So I'm going to plot the molar magnetization in units of Na mu b versus field. You can also plot that same plot, so 2, 4, 8, 80, 200, 300 Kelvin. You see how these curves are changing? You can plot that in what's called the reduced field axis and see that every single curve overlays perfectly. If and only if the zero field splitting is 0. As soon as it's not, these are about to be perturbed. But the point I want to make is that the reason that we plot in this reduced field axis is that this is easier to kind of tell how these perturbations are happening. And so over here, we're 1 over T, so these are the low temperatures and high fields. These are the small fields and high temperatures where we're usually thinking about magnetic susceptibility. But you'll notice that this follows that Brillouin function, right? This is a magnetization curve. Now, oops. Nesting. Not that kind of nesting, but nesting. Yeah, look, I still can't really tell what's going on if I don't reduce the field axis, but if you do, and unfortunately cyan is also poor color choice here, but you can see hopefully a curve there, a lighter blue curve, and this curve. And if you look really closely, you'll see all the high temperature curves are like way down here, but they fan out from each other. And another public service announcement, by the way, when I think of nesting, I think of something like, overlaid. And I think whoever used the word nesting here has the definition backwards. So don't get confused. When these magnetization curves fan out, that's called nesting. When they are overlaying each other, that's called lack of nesting. So we're going to define it that way. Okay? Sorry for that. Now, you can do these types of measurements where you have iso temperatures. You can also... Oh yeah, one thing, sorry. So you can see that the -10 wave number case has a different kind of behavior than the +10. I'll go back and forth. You can see -10, +10. They behave differently only at these low temperature, high field limits. Over here, look, these are not changing. You can't tell the difference at these high temperatures. So you have to go to as low a temperature as possible to see the difference for this S equals 3/2 system. Now, there are 2 different types of magnetization measurements you'll be able to do. You can do variable field fixed temperature, VH/VT, or variable temperature fixed field, VT/VH. And actually in Milheim, we're usually doing this one. Before I came here and I was at Madison, we were doing this one. They give equivalent results. The only real advantage, I would say, of the VH/VT is if you have a really large zero field splitting. Keep in mind that most magnets can only go up to like 10 Tesla for a squid magnetometer, which is about 10 wave numbers. But if you have a really large zero field splitting, maybe it makes sense to have a really large range of temperatures you look at just to help populate those higher Boltzmann levels. So this type of measurement on the left is more advantageous if you have a really large zero field splitting. But otherwise, you should be able to get similar information from each one. Okay? And so, yeah, you can do it with iso fields, but it's the same type of information. And these correspond to the exact same types of zero field splitting between these 2 plots. I didn't change anything. Now let's go to one more thing. As Frank mentioned this morning, there's actually really physically no such thing as exchange, but we're often pretending it's kind of like an energetic interaction. And so there's a Hamiltonian associated with that. And you can look at 2 uncoupled doublet spins, for example, and create a spin ladder based on this Heisenberg-Dirac-Van Vleck Hamiltonian. Now, in Milheim, we're typically using the -2J convention, but be aware, I've seen the -J convention, the +J convention, and I think I even one time saw the +2J convention. There are 4 possible conventions out there. The most important is truly the sign, because that controls if it's AF versus ferromagnetic coupling. And then the 2 is important for the magnitude. That just tells you the spacing between the total spin levels on the spin ladder, okay? But this is how 2 individual spins can couple together on 2 different spin centers to create a Gestalt property, this total spin. That's the Heisenberg spin ladder. And with our sign convention, if J is negative, that's anti-ferromagnetic coupling. So the spins are coupled with opposite spins, individual spins of each other. And so the lowest possible total spin is the lowest energy. And the opposite is true if J is positive. That's called ferromagnetic coupling. So now the spins are cooperating. That means that this picture would be inverted, and the total S equals 1 spin would now be the lowest in energy. So you would just rotate about that axis and get an inversion of the energy levels. Okay. So how does that look like? And again, you can work this out with the Van Vleck formula. I've kind of already done that for you just to focus on how these curves look like. But you can see in the perfect world, for 2 S equals 1/2 centers, 0.376 times 2 gives you just this red line here, okay? And there's no coupling. If they couple ferromagnetically, you get this blue curve where at the low temperature, you're only populating the total S equals 1 spin state. And it approaches chi t equals 1, which is what S equals 1 should be. It's just at a high temperature, you start populating thermally this S equals 0 state, and so you start to approach an asymptotic behavior that would eventually, if you went to infinite temperature, line up with that red line. And the opposite is true for the antiferromagnetic couple case. If you go to low temperature, the lowest populated state is S total equals 0, so that's diamagnetic at low temperature, right? But if I increase that temperature, I start Boltzmann populating S equals 1, right about maybe 20 Kelvin, let's say, and it keeps getting more populated, more populated, more populated, until, again, you reach an equilibrium where, right, the Boltzmann population will approach that asymptotic behavior. That's fundamentally how that looks like in chi-t, okay? So if you see that type of effect, you might have an idea that, especially if you know you're working with like a dimer or, you know, even a oligomer, you know you might have some coupling between your spins in your system, right, if you see that type of behavior. And so the most kind of famous example of this is the Bellini-Bowers example, where they have this copper acetate paddle gel compound, and there's no bond between the coppers, but they are interacting weakly weakly with respect to a chemical bond strength, let's say, but, you know, relatively strongly in terms of exchange. And that's to say that if I go to low temperature, they're clearly antiferromagnetically coupled because chi-t goes to 0, right? But if I go to high temperature, well, I start populating S equals 1 more and more and more and more until it's eventually going to level off, right? That's how that works. And you can actually model these experimental data points and determine how strongly are they interacting. That's a direct example of how modeling this type of data gives you an extremely useful piece of information. And you can even look at the high temperature limit and see how are the G values deviating away from the free electron G value, right? Because copper being D9, the spin-orbit coupling acts in such a way that it actually tends to supplement the G value to larger values. If you have less than half-filled D shells, it tends to go the other way. So maybe something like titanium might have G values that tend to go less than 2, right? But copper, being D9, in this case, is going to go to G values that are larger than 2, typically. Okay? That's how that works. And so now let's put it all together. This is a paper from my PhD, collaboration with the Fiedler group at Marquette. Praveen Kumar was a synthetic chemist, and, you know, I did the magnetometry here. But in red are these experimental data points. I measured, you know, over a large temperature range, and I plotted chi-t versus t. Now, what we have is a high spin cobalt-2 spin center here, S equals 3/2. But we also have this ligand radical, that's S equals 1/2. But these two local spins, well, they may or may not interact. And how do we know if they interact? We'll do an experiment like susceptibility, and we'll take a look at that. And sure enough, we see this big deviation, especially at these low temperatures, from the Curie law. And it looks like it's going to 0 without even doing a model. If it's going to 0, what's the sign of the coupling? Is it ferromagnetic or antiferromagnetic? I didn't even have to do a fit. It's antiferromagnetic, because why else would it go to 0? That's the reason, right? No modeling required. You can just look and see. And if I had two uncoupled spins, that's what this dashed line would be. But it's clear that they're in the high temperature limit, right? These G values must be way larger than 2. And that's quite typical for cobalt, right? Cobalt-2 likes to go to really large G values, actually. It has a lot of spin-orbit coupling. And this is actually kind of an extreme example. When I say that these are very large zero-field splittings, these are very large. Typically, you see something more like tens of wave numbers, but cobalt, you can actually see things in the hundreds of wave numbers regime. So that's why, you know, we're able to really model this. And what I did is I said, look, and you'll see this tomorrow in the EPR lecture, but we often say G perpendicular, G parallel. Parallel means Z, perpendicular means X, Y. Okay, parallel just means with the field. Typically, we call that the Z direction. And you'll see that there's a G matrix that's anisotropic in the sense that the Z direction is different than the XY directions for both of the molecules I looked at, right? I said, this is an organic radical. I'm going to assume it's G equals 2. I didn't actually model it, but it's a good assumption, okay? This zero field splitting here, this G tensor anisotropy of the organic radical is really small compared to the transition metal, so that's why I did that. And then I modeled the zero field splitting parameters and then this exchange Hamiltonian, and I can look at the difference in coupling strength between swapping out a nitrogen for an oxygen, right? That's kind of cool. That allows us to understand something meaningful about how does a chemical perturbation lead to an electronic structure perturbation in my systems. And so I'm considering, you know, these would be very complicated Van Vleck expressions if I wrote them out on paper, but luckily we have programs that handle doing this modeling for us, okay? There is this TIP parameter, which I mentioned earlier. That's just because we're not leveling off. And so we're saying, oh, yeah, okay, we're going to correct for that. That's what the TI parameter does. It's a bit of a fudge factor that we include in our models to correct for the high temperature behavior not leveling off at a constant value. That's what it's for. Okay, how about example 2? Let's go back to the tetrairon example. This is like all hell breaks loose. Now we've got 4 spin centers to look at. So spin center 1, spin center 2, spin center 3, spin center 4. I have to now account for the exchange coupling between nearest neighbors. So 1, 2, 2, 3, 2, 4, maybe next nearest neighbors, and maybe, if I was really sophisticated, next nearest neighbors. That's a lot of different exchange couplings. Then each iron has its own G tensor. Each iron has its own zero field splitting tensor. And all those things are going to work together to create this crazy chi-T curve and these magnetization measurements that we did. But we can model that. And what we see are that the outer 2 irons have negative zero field splitting tensors. The inner 2 irons are actually positive zero field splitting. We can look at their, I'm going to use G1, G2, G3. I'm sweeping an issue under the rug here that Frank brought up. There's nothing that says that the molecular XYZ frame it doesn't have to align with the zero field splitting tensor frame, which doesn't have to align with the G tensor frame. These coordinate systems could all be related in whatever orientation they want. And there are Euler angles relating these, so that's why I'm using G1, G2, G3, and not XYZ, because we don't actually know what is X, what is Y, what is Z here, okay? And luckily, I didn't have to do next nearest neighbor models, just a nearest neighbor coupling, or really actually more accurately, Alessio did this. But when I was talking with him about this, he didn't have to do these next nearest neighbors exchanges, just the nearest neighbor exchange was enough. So you have 2 ferromagnetic interactions between the outer 2 pairs of irons, but the inner 2 pairs of irons are antiferromagnetically coupled. Very weakly, but they are coupled, okay? That's how this was modeled. That's what happened. Whew, that was quite complicated. I'm going to shift gears. What about interactions between molecules? We're not just looking at molecules, we're looking at molecules that also exist in a solid state, and they're probably, or sometimes, going to interact with their neighbors. We handle this with what's called this sort of Weiss Hamiltonian, where we use a sort of mean field approach and say that the Z component of the spin that we're interested in kind of feels an average value of its environment, of its Z spin of the neighboring environments, okay? And Z here is actually a different Z. It's the number of nearest neighbors that actually is touching that. And then minus 2J is the convention we use. But that's basically it. And what we can do is we can modify the Curie law to what's called the Curie-Weiss law and put this perturbation term in the denominator, which is also sometimes symbolized with capital theta, but they're equivalent. So theta and 2zj, these are equivalent ways to express a similar idea. But again, if I just look at this simple equation, we're using that a positive value are ferromagnetic coupling between molecules. A negative value is antiferromagnetic coupling between molecules. So not only can you have coupling within a molecule, that exchange can happen outside of molecules too. And that's what this accounts for. I will warn you that in the older versions of the ULX software you use today, 2zj is broken, so don't use it. Only if you're a Windows user using a new one, I fixed it. I could not figure out how to compile for Mac or Linux, so what I've done is we're all going to use theta, okay? But you could convert on your own to 2zj and you get the same answer. And what does that look like? Well, again, kind of similar in the sense that you see how if theta is minus 5 Kelvin, so yeah, theta is in units of temperature, see? But zj is in units of wave numbers, so that's a key difference as well. You can see that AF coupling between molecules leads to a decrease in chi-T, ferromagnetic coupling leads to an increase. And often, the way people actually model this is to look at 1 over chi, yet another plot. That's called a Curie plot. So the slope is the inverse of the Curie constant, and then the x-intercept is actually going to tell you what the Weiss constant is in your system. So if you have no intermolecular coupling, it should go to 0. But if you see an x-intercept, you have a good idea, hey, I might have an intermolecular interaction that I need to account for. And so this is applicable to bulk materials. So here's the Curie law for a paramagnet. Here's how it looks for a ferromagnet. We call that the critical temperature. An antiferromagnetic, we actually usually call that the nail temperature, but it's essentially the same idea. And this is yet another paper for my PhD, anti-ferromagnetic ordering and a zeolitic imidazolate framework. Look, we're not dealing with a molecular species, we're dealing with a moth, and these metal nodes you can think of as being these kind of molecules interacting with each other intermolecularly. So you can think about at very small thermal energies, you have a very AF ordered lattice, but as soon as you go above this nail temperature, you end up at a large disordered lattice that begins to approach that carrier behavior again. And you can even see 1 over chi in red. I can plot that x-intercept out and see, but the experimental data deflects. So that's how you can actually tell what's going on. One public service announcement, you have to take extreme care interpreting your data, as always. Based on everything I just talked about, what does this look like? You have this kind of behavior where it seems to go up at low temperature. Any ideas? Yeah.
Ferromagnetic coupling?
Yeah, right. This looks like ferromagnetic coupling. You have to be careful, and I'll tell you why. Let's look at the compound. This was done by Amelia Wheaton, also in the Berry group. She's at Argonne National Lab now. This is a dimolybdenum iron compound, so there's a quadruple bond between the dimolybdenum core. And if I just draw the MO diagram for the dimolybdenum core, you'll see that that quadruple bond, everything is paired up. There's no unpaired electrons there. If I perturb this MO diagram by adding the iron, 5 unpaired electrons are on the iron. This is the total MO diagram of the system with all the symmetry labels, since we love group theory. And I've used the lowercase symbols because we're dealing with orbitals, not states. But look, 1, 2, 3, 4, 5 unpaired electrons, but they're on the iron. But wait a minute. It looks like ferromagnetic coupling, but what is it coupling to? Because this is a diamagnetic core and we just have a single spin center. So what ferromagnetic coupling? Well, could it be intermolecular? Nope. What happened? What went wrong? Why does the data look so weird? I mean, this is beautiful, but it means nothing. And the reason for that is I told you that chi can be anisotropic in the x, y, and z directions. And what's happened here is that this sample was actually microcrystalline. It was not a powder. What that means is that our measurement was not sampling a powder orientation. It was sampling an orientation. I think these were plates, so I think it was actually sampling along XY orientation, if I'm not mistaken. And so how do you correct for that? You can take this and put it into icosane C20H42. It's just candle wax, basically. You can melt the powder, the microcrystalline powder into that, and all the molecules won't stack up like plates. They'll be randomly oriented like a powder. And if you do that, look at the curve in red. It's completely gone. There's absolutely no ferromagnetic coupling in this system at all, period. That is wrong. And it's only the data in red that has any meaningful physical parameters. If you fit the black curve, you'll get some nice values that have absolutely no application to this system. So my public service announcement for you is this. If you see a chi-t curve that looks like that, or looks like AF coupling, why don't you grind up the crystals in the glove box, put in an icosane and do the measurement again, and just double check it, because it might not be. And especially for a system like this, that makes no sense. So you have to take very great care to interpret your data. You could be easily misled by something that's a trap like a microcrystal. And I would say magnetometry is one of the few techniques where I prefer to get powders and not crystals. So for people who have trouble growing crystals, this is your ticket. Okay, I think, let me see what we're doing on time. I think I'm going to stop here because the other things don't really apply much to molecular species. And if you want to look at the lecture notes, I talk a little bit about like single molecule magnetism and alternating current susceptibility, which we won't do in the practical, but I think that's a good place to stop. So if you have questions, we can stop here, I think.